Swayam Prabha. Digital India. Educated India.
Welcome to the second lecture of production of vacuum, that is second module, and we are going to describe a very important pump, which is rotary vacuum pump. This is the most popular vacuum pump which is being used almost in everywhere, in industry, teaching laboratories, R&D laboratories, space organizations, nuclear, everywhere. It is a very fundamental pump, I would say, and it encompasses all concepts related to production: compression, expansion, sweeping, positive displacements, inlet pressures, filters, and various types of mechanisms which are common to various pumps. Somewhere or other, lubrication, degassing, all these concepts are involved in this pump. So, it is customary to start production of vacuum with a most fundamental pump known as rotary pump. To be more specific or scientific, it will be called rotary vane pump, because there are rotary piston pumps also, and high speed rotating turbine based turbomolecular pumps are there. There are many pumps which depend on rotation, that we have discussed in classification also, positive displacement pump as well as entrapment pumps. So, these are positive displacement pumps. So, what we will be discussing in rotary vane vacuum pump are the concepts related to introduction of the pump, some constructional aspects, because best way to understand any machine or any pump is, first, like a layman, you try to see what are various sub components or elements in that component, in that pump. So, if you know the construction, you can easily understand the action. If you are a teacher, first if you try to explain action and then construction, that is one way of doing it. But in a typical engineering industrial atmosphere, people are interested in developing these products based on construction and then operating principle. These two go hand in hand. And at the end, we will also see its characteristics. What is the characteristic of a pump? Pumping speed and how it varies with pressure. So, that comes under pumping speed variation, which is common for most of the pumps. This being the first pump, most of it is explained here, but similar concepts are there in other pumps like gas blast, pumping speed variation. These two are there in almost every pump, particularly medium vacuum. Very high vacuum and all gas blast will not be there, but pumping speed variations will always be there. As a teacher, I can ask what will be the pumping speed at the ultimate vacuum. Apparently, equivalent pumping speed is 0, because pump is running, but vacuum is not improving. So, there is nothing that is being pumped. So, what is the concept of pumping speed? So, it starts from a maximum value which normally manufacturers quote. Naturally, if I am a manufacturer, I will quote maximum value. I will not quote the 0 value, nobody will purchase my pump. In between, there will be variation of the pumping speed. Now, you have to decide as a design engineer at what vacuum level I am going to operate my application and what level of constraints are there to maintain the vacuum or to pump down it in a faster time. Some people may want vacuum in 2 minutes, some people want same vacuum after 20 minutes. In industrial production, particularly IC chip manufacturing, the silicon wafer is being transferred to a small chamber initially, that is a cleaning chamber, where the silicon wafer is being cleaned and then it is transferred to the main process chamber for further processes. So, that initial chamber is evacuated very fast. It is alternatively exposed to atmosphere because you have to open it and take the slide and again put it back. So, such applications high speed is required. There are some applications like small bulb and TV tube evacuation or X-ray tube evacuation. Your quality of vacuum is important. It does not matter if it comes instead of 5 minutes, 20 minutes, no problem. But in a filtration application, I want to increase the speed, so I may have variation towards higher side. So, pumping speed specification has to be decided by the design engineer based on the application. First of all, which pump to be used, whether rotary pump or some other water ring pump, that is one design issue. Once you decide a particular pump based on experience and based on what is going on in other countries and other places from the literature, you have to decide locally what will be its capacity. Capacity is nothing but pumping speed at that operating pressure which is required for an application. That is all an engineer needs to know. Most of the time we do not have to understand what is there inside. Anyway, if you make a phone call, that company fellow will come and repair it. Do not venture into opening a pump for repairing. Though I will tell you some troubleshooting, but it is more of a maintenance so that it will never come to that trouble issue. You have to take care. There also it is a part of troubleshooting, maintenance issues like lubricating properly, etc. So, finally, we will see a particular subsystem called gas ballast, which is very important in rotary pumps because historically this has been developed when there was a constraint of using these rotary pumps in the rainy season. When water vapor is there to be pumped, not just dry gases, pump is stalling, it is not working. So, we will see what is this towards the end, and we will also give you some idea of single stage or double stage pumps depending on the level of vacuum and depending on the investment cost. 2 single stages parallelly may be required in some applications where pumping speed at high pressures are faster. They do not require a very good vacuum level. Some people say, I need very good vacuum level, I do not mind slowing down. For that, it is 2 stages connected in series will be better, not parallel. So, these issues also will be discussed. But most important is principle behind that. From the principle, what we will know, what are those volumes, whether it is a dead volume in the compression zone or a sweeping volume or sucking volume in a rotary framework of stator and rotor combinations separated by vanes into different volumes like suction chamber, sweeping chamber and exhaust chamber, somewhat similar to your compressors and IC engines type. Similar things here. It is not a reciprocating machine, it is a rotating machine. That is why it is called rotary, and based on vanes, that is why it is called rotary vane pump. Its specifications are related to working principles. We will see that. The figure gives you a clear idea of how a rotary pump looks like. Several companies manufacture these type of pumps, both in India and abroad, very high qualities. Depending on the sophistication and controls and types of materials that we use and so amount of sound that it produces or the heat that is being generated or the apparent aesthetic look or a longevity or a motor rating, you have different companies giving different quotations, because if you want to have a high quality pump, naturally you have to spend more money. But if you are having a rough application of 10 tar and in a dirty atmosphere you are handling, no point in purchasing a highly sophisticated pump which produces 10 power minus 3 tar and it should be very clean room type of equivalent thing, no point. With that cost you can purchase 10 pumps at 10 tar operating type. So, a judicious decision will be taken by the engineer whether you go in parallel combination or a series combination or a low cost or high cost, what is your investment, like that. It is more relevant in the present day society because many people are thinking of making startups. So, in the initial stages their startup investment may not be high. So, you can easily have a startup with a small rotary pump with a small application, with small amount of vapors coming out or process vapors, like a very like a small application like a bangle coating. You can start very small investment. I am just talking all these things when I am explaining pump, because pump forms the main cost of any application. So, this is the typical pump. This can be used as a main process pump to produce vacuum, or it can be used as a backing pump to some other high vacuum pump, because this vacuum pump cannot produce 10 power minus 5 torr minus 6 torr required for X-ray tube or electronic industry or space or nuclear. That time this is used as a initial pumping to an acceptable level of vacuum. It will be taken over by the high vacuum pump. But I am telling you, high vacuum pump requires the helping hand of this rotary pump. That is why it is called backing pump. If you do not evacuate to 10 power minus 2 torr, high vacuum pump will not further take it to 10 power minus 2 to 10 power minus 6. So, high vacuum pump is only a fine vacuum which is removing few micrograms of gas. Grams of gas has already been removed by this mechanical pump, but it may be much less cost. It may be 10,000 rupees. High vacuum pump which is removing only few milligrams, a turbomolecular pump, may cost 20 lakhs. Why? Because it is trying to do at a finer level. So, pumps at high vacuum, their operating principles are different, their type of materials being used different, whereas this is a medium vacuum pump, but it is 100% required even for high vacuum pumps, because somebody has to initially produce a level of vacuum from where the high vacuum pump can take over. So, rotary pump is a base pump which produces vacuum, good enough vacuum for a particular application in totality, or it can produce a backing vacuum so that high vacuum pump starts, after that process starts. It can also take help of another pump called roots blower, together will be forming a backing action to a high vacuum pump, depending on loading situations. Very large scale vacuum metallurgical furnaces, rotary pump has to produce minus 2 torr so that diffusion pump will take over, but it has to produce very high speed, very fast, and later it has to match to the diffusion pump exhaust conditions. So, it requires a boosting of this rotary pump by a booster called roots blower. That time the roots blower and the rotary pump together, called a booster stage, is acting like a backing pump. But in all these conditions, 99.9% of the gas has been removed by this fellow only, but no application started, and it is not costly also. So, that way rotary pump should be understood as a main workhorse which can remove lot of gas from mass point of view, which can create conditions for the high vacuum pumps to take over. This pump quality and its lifetime and its variation in pumping speed, you have to decide based on your budget and your application. Okay. And single stage, 2 stage varieties of pumps are available. You can produce a level of vacuum up to 10 power minus 2 torr or 10 power minus 3 torr, like that, without loading. That means it is a closed volume, you removed it, you got that vacuum. But under loading, it will not be that much vacuum, because continuously some external source of gas is coming. I explained you in the throughput concepts, that is called gas load conditions. Initially, pump has got a load only from the interior volume of gas that is available in the chamber to be evacuated, that is pump down time. But after that, when it reaches to the extreme or ultimate levels, it is only the background that is continuously coming gas molecules, is called gas load. It can be due to leak, it can be due to degassing, it can be due to real process that is taking place like CVD, PVD, then or chemical distillation, etc., and they will be handled by the same pump. Okay. So, what is the working principle of it? When you are trying to understand principle of any machine, you do not think too many things at the same time. First you take constructional aspect, like in a mechanic test, first they will do identification of the components, then some knowledge questions in Viva, followed by some trade test. So, something like that, when you are trying to understand these mechanical pumps, you have to first understand the constructional aspect. So, come to this construction, look at the figure now. It contains a rotor, that green looking thing. I think my mouse is there, okay. And this rotor has got a diametrical slot cut, not a total cut, and there will be some full portion. So, it is a diametrical slot in the working chamber, it is a cylinder, and in that slot two vane type of structures are there. That is why it is called rotary vane pump. If you look at that vane, I hope my cursor is able to go there, yeah, this is the vane. There is another vane. These two vanes are supported by a spring, so that centrifugal force plus this force will try to keep these vanes always touching the inner lining of another chamber called stator. So, this rotor is basically situated in a eccentric fashion in the stator. That red colored thing is stator, the green colored thing is the rotor. Rotor is having a diametrical slot in which two vanes are there supported by a spring for the mechanical integrity, so that they will always be touching the interior portion of the smooth, very highly polished lining of the stator. And top, it is eccentrically situated with a small micron gap. That gap will be filled during the running condition by the lubricating oil, and very fine gap, even though lubricating oil is a liquid, it will have enough energy to withstand the pressure drop. That is why it is called top seal. So, in a working condition, there are three touch points, physically two touch points, but third top seal also looks like a touch point with an interface of oil. Three touch points in a rotary frame will create three volumes. If it is a concentric, there will be top and bottom, two annular structures, two moon-like structures in the annular gap. In order to have three structures, we have to have a eccentricity of the rotor in a stator. If somebody asks why rotary is eccentric in a rotary vane pump, you should immediately say then only in a rotary frame with two vanes and one top seal, three touching points varying with top seal will not vary with time, but these touching points of vanes will vary. You will start getting three volumes. One is a suction volume, one is a sweeping volume, one is a compression volume. That is the reason it is to be eccentric. Any mechanical motion, when it is touching and gliding, there will be frictional heat. So, there will be cooling required, there will be lubrication required. So, this machine is designed with a lubrication concept. So, there will be oil requirement is there, which is filled in a crankcase. That blue colored box contains the oil, the dotted things are oil. This oil, it will act like a coolant, because this is a relatively high pressure, there will be heat of compression, that compression heat should be removed, otherwise seals will be spoilt after some time, after 1 hour running. It will act like a coolant. It will also act like a sealant, because entire structure is working under vacuum conditions. Atmosphere will try to rush in through any possible leaks in the integrating of various subparts of the rotary pump. It is not an easy joke to make a leak tight pump. So, you require an oil which is acting like a sealant also. And finally, in a mechanical motion, there will be wear and tear. So, you also require a lubricant. So, if there is a question, what is the role of oil? It acts like a sealant, it acts like a coolant, it acts like a lubricant. Okay. Then, if you carefully observe, there is one inlet condition, there is one exhaust. So, inlet and exhaust on either side of the top seal. Entire chamber is submerged in a oil container, and this interconnecting pipe, this is inlet hose, is connected to the chamber to be evacuated, and the exhaust is to be connected to either exhaust. If it is allowed, it is open air, otherwise you connect it through a pipe and through the window you take it out, otherwise some oil vapors may come out to the room and get smell. So, in one rotation, you will get 2 times some sort of moon type of volume, and number of rotations, if it is n, 2 into Vn will be the pump displacement. This we will see later when you look at the working principle. So, this is basically a constructional aspect. Now, look at the figure now. There are 4 stages of operation. Basically, rotor is rotating and it starts with first phase induction. That black colored thing is being, that is nothing but the air molecules getting filled and coming from the chamber. Okay. This is called induction. Second stage is, once this vein comes to that, that vein comes to that, then is called isolation. That means some particular amount of gas has been removed from the chamber and it is isolated. Then third stage is, it gets compressed and the exhaust valve which is there, which is a flap valve, other side atmosphere, it opens when the inside pressure is higher than the atmosphere, it opens. So, induction, isolation, compression and exhaust. These 4 stages are built in a operating principle of a rotary vane pump. Well, I can keep on talking how this comes in a most elementary way, but I am sure any person who has completed his +2 after schooling, they will be able to understand these principles, because there are several textbooks which have explained these things very much in minute detail. It is basically an eccentric rotor with 2 vanes and with 1 top seal. When it starts rotating, there will be induction of gas, that is nothing but sucking of the gas from the chamber to be evacuated. There will be isolation of a particular amount of gas, and that will be further compressed and exhaust is opened, and you will start getting slowly vacuum in the chamber. Initially 760 tar. One small element of gas has been removed, then you will get 752, 758 tar, then 750, 700, 600, 500, 300, 100, 10, 1. Afterwards 10 power minus 1, 10 power minus 2. How long it will keep on going? When the suction is taking place at 10 power minus 1, at the exhaust pressure, even after compression into a finite dead volume, pressure may not be more than atmosphere. Then exhaust valve will not be opened. So, you will not get better vacuum than that. So, it will be temporarily staying there and exhaust valve is not opened. As soon as this vane crosses, it will re-expand back into the chamber. That is why there is a limitation. So, how do you overcome this limitation? Instead of connecting to the atmosphere, you connect it to another stage of another pump. Then this pump will act or will feel that there is an atmosphere of already 10 power minus 1 tar created by another pump which is connected to its exhaust. That is called 2 stages connected in series. Then you will get better vacuum. But there again another pressure level, another vacuum level will come, it cannot be more than that. Again exhaust valve will stop. So, again pumping action ceases. So, you cannot create 3 stages, because at some stage the oil that is being used as a lubricant itself will produce some vapors. So, you cannot get a vacuum better than that. So, it is customary to use 2-stage series connected pumps. But if your vacuum level itself is 100 tar, you do not require 2 stages. So, if you are connecting 2 pumps in series, instead you connect them in parallel, both of them will be sucking the higher pressure side, 10 tar operating pressure, pumping speed will be more. So, pumping speed is given by this isolated volume in 1 stroke. 2 such connected volumes will be there in 1 rotation. If number of rotations are n, 2 into V into n. 2 is constant, V is constant, n is constant. So, they should have pumping speed constant of pressure, but it does not happen, because as time passes, as vacuum starts improving, the top seal cannot withstand that much pressure drop. There may be some leak, there may be many leaks coming from various portions, and there may be degassing from this portion. There may be compression issues, that exhaust valve is not opened, all cycles are not called duty cycle. All this together will make the net displacement 0. So, pumping speed is not there, but still you may have to run the pump because there may be small leaks which it is compensating. So, for running conditions you may have to run. Accordingly, the electrical power also may come down because loading is not much. These issues cannot be discussed in a limited time. Later when we discuss with process applications, again we will discuss rotary pump, we will see in the cost issues, etc. So, just whatever I have explained, I just want you to see an animation. So, right side suction is going on, then there is a isolation like that, then again compression. See, suction, isolation, again compression. So, this can give you beautiful animation of how rotary vane pump works. And instead of connecting exhaust here, you can connect the inlet of another pump. That way you will get a two-stage pump. So, they are designed basically to produce vacuum of the order of 10 power minus 2 torr. The lowest pressure in a rotary pump is decided by the compression ratio, and which is very high. You are evacuating at 10 power minus 3 torr and producing up to 10 power 3 exhausting. So, 1 lakh compression, 10 power 6, 10 lakh compression, but heat of compression is not much because it is a rarefied conditions and moles are not much. Normal compressors only have 20 compression ratio, but lot of heating effects will be there. That is why in isothermal compression, a Carnot cycle or anything, if you want to make an ideal thing, you have to have aftercoolers, intercoolers. Here we do not do that, excepting the crankcase oil which is taken by the natural convection, etc., which is acting like a coolant. We are not bothered about heat much. Of course, it is better to keep it in AC room. It is better to connect the seal, whatever is the crankcase, with little bit of fins, extended areas, etc. Okay. So, you try to design various aspects in vacuum pumps to put various levels of vacuum or various levels of pumping speed. With all these things, if you look at the left side, pumping speed falls as a function of pressure. At some pressure, it reaches ultimate. If you put 2 stages, it will be better vacuum. So, exhaust is either it is connected to another pump or it is directly exhausted to atmosphere. Depending on that, pumping speed variations are there. Right side, we have connected it. Inlet of one pump is connected to the exhaust of the other pump. These are called 2 stages. In actual practice, these two are connected to a common shaft with a phase shift of 90 degrees. And actual construction we will see later when time permits, when we discuss with process applications or maintenance issues. So, at the best you can reach 10 power minus 4, which is ideal situation. Under loading it will be minus 2. So, if you want to get better vacuum, you have to go to diffusion pump using this as a backing pump. Okay. So, before we complete the rotary pump, there is one small problem. If the vapor are there instead of gases in the chamber, during the compression zone, what happens is the vapors get condensed if the pressure existing at that compression zone is crossing the saturated vapor pressure. So, it may not be acting like a gas and lift the exhaust valve and go out. It will be forming a small droplet. Then droplets follow gravity rule. They do not go upwards. So, they will never be exhausted, and again it will come back and it will evaporate once the vane crosses, re-evaporation. It will be continuous process. You will never get better vacuum than the vapor pressure of the water at room temperature, let us say 20 torr. So, pump is running, you are supposed to get minus 2 torr, you are getting only 20 torr. What is happening? Because your chamber contains lot of water vapor. That was a rainy day, you have exposed the system to the rainy day, lot of water is there. After initial removal of air, dry air, nitrogen, oxygen, at the end now water is being removed, water has been evaporated under that low pressure, it has come to the suction port, it is going to the sweeping port, finally in the compression it is liquefied and it is not getting exhausted. So, this has become a problem, and there was a famous saying that in winter you will not produce vacuum. But later engineers do not keep quiet. No, mechanical engineer with a chemical background, what he did was, during the exhaust stroke, before the partial pressure approaches the saturated vapor pressure, you try to leak in some dry air. That means, you are spoiling the vacuum level much before the vapor conditions reach the saturation conditions. Then what will happen? These background air molecules, they will be floating these oil molecules, that coalescence will not take place, drop formation will not take place. This is apparently a small concept, has solved the problem of throwing away the vapor, allowing them not to get coalesced. You are trying to confuse them to make a microparticles under a background flotation of air molecules by letting in the dry air, which is popularly known as air ballast. So, once you cross getting 20 millibar, you try to open the air ballast in the exhaust conditions in the compression volume, and you try to spoil it, run it for another 20 minutes. When the water vapor is thoroughly removed, again you can close it. At that time only the dry air leaks and all being handled, you will get 10 power minus 2 tar very safely. Of course, this principle of air ballast is very nicely explained in various books. Animations are also there. I leave the reader to understand these concepts, but in any case, if you are in doubt, later we will see in the quiz series, etc., or if you can contact me, I will explain you, because air ballast is a very good operation which has created a lift to the sales of the rotary vane pump in rainy seasons. Okay. So, but when you are blasting, you are loading unnecessarily, you are not only removing the molecules, you are adding some molecules. Effectively, pumping speed is coming to 0 at higher pressures. With and without ballast, single stage and two stage pumping speed variations are given here. So, this you can easily slowly read it. With and without gas ballast, what will happen to the ultimate vacuum, what will be happening to the pumping speed variations with pressure. And but whatever is there as a constant pumping speed up to 1 tar, that is what most of the time manufacturers will give you. That is the real positive displacement pump. If you are interested in 10 tar or 100 tar for mechanical applications, you do not have to bother about all these things. But if you are coming to 10 tar, 20 tar for drying applications, you have to care little reduction, but air blast operation. If you are coming to 10 power minus 2 tar in a dedicated pump, you have to also clear degas systems, etc. Some precautions have to be taken, we will see in the application. If you are using it as a backing pump, you have to adjust such a way that pumping speed at the backing port of that high vacuum pump should match to the throughput of this pump. Throughput of this pump means at the exhaust condition of the high vacuum pump, this pumping speed multiplied by that pressure should be same as the inlet conditions of a diffusion pump, that's pumping speed and its pressure. P1 V1 should be same as P2 V2. We will see when we are discussing with diffusion pumps, etc. So, pumping speed variations are very important issues in rotary vane pumps, where engineer has to properly design depending on the application. Okay. So, advantages, disadvantages, pumping speed variations with and without oil, so many aspects are there. In fact, last 20 years dry pumps have come, that we will see in next section, replacing these things in certain very important applications where oil is not allowed, water vapor is not allowed. Certain things are coming up like that in pharmaceutical sectors. So, dry pumps have become equally popular, but rotary vane pump is always number one, because it can do by itself lot of operations, respectable vacuum. With booster it can create -3 tar, with a roots blower it can also act like a backing pump to anybody. So, it is a universal almost like a rice in a lunch, it is required. You can have variations with many other items, but rice cannot be varied or bread cannot be varied. So, like that rotary vane pump is a very, very popular pump. Thank you very much.